Hello, ICP. This is Mr. Jacobson again, and now we're doing notes on section 5.4. And in section 5.4, we'll be talking about springs and spring potential energy and law of conservation of energy, mostly when non-conservative uh, forces and work is not considered. But we'll talk a little bit about when non-conservatives come in as well. So here I have a diagram of a spring. This little squiggly line is supposed to be a spring, and this is a frictionless surface. And if we push this mass in and release it, the object will oscillate back and forth. It will be at its fastest point as it goes through the equilibrium point, slow down and come to a stop, and then accelerate back, reach its fastest point when it hits the equilibrium spot, and then slow down when it gets over here, and just go back and forth like this forever. Now, to get this mass off of the equilibrium position, we need to apply a force. If we apply the force on this side and push it to the left, we will cause the spring to compress. If we apply the force on this side and push this way, we'll cause the spring to stretch. Well, over here, I have an example of a graph with just made up numbers for a spring. And I am applying a force on the left side and pushing the mass to the right. And I plot my points that I see when I do that. And then I draw the line of best fit. And I will notice that the force is directly proportional to the stretch. In other words, I have a straight line going here. Now, if I would take and apply the force and push it to the left, I would see that this line would extrapolate back this way. And so the slope of this line will be continuous, whether I'm on the right side or the left side of the equilibrium position. Now, the slope of this line has been given the term the spring constant. And you'll notice that the line is straight. But that's if I stay within the elastic limit of the spring. If I were to take this and pull it far enough, this would become permanently distorted. And then what would happen is the line would go like a straight line like this, but then it would curve off like that. That's a little bit too flat there. Let me erase that and try again. So it would go like this. And then when we released it, the spring would go back like this, and it would not return to its original position. And now we've ruined the spring. And you've seen this like on screen doors where you have a spring that's been stretched beyond its elastic limit, and you'll see that the coils aren't uniform. You'll have a stretch in the coils over part of the spring. That is not good. So when we do this, we're going to be talking about cases where we're staying within the elastic limit of the spring, and then this line will be straight. So just so you're aware, this line doesn't go straight indefinitely if we exceed the elastic limit. Then we have Hooke's law, and Hooke's law says that displacement stretch or compression is directly proportional to the deforming force, which is exactly a restatement of what we saw with this graph here. But now this applies not only to springs, this applies to anything. You could take a steel beam, put it in a building, and then have a bunch of people stand on the floor that the steel beam is supporting, and the steel beam will flex. And then when the people leave the floor, the steel beam will go back to its rest position. And so this displacement, stretch, compression, any type of deformation of any type of solid will follow this unless it goes beyond the elastic limit, and then the beam or the spring or whatever is permanently distorted. So then this is an equation for Hooke's law where, again, it's just simply restating what we saw with the graph. The spring force, often referred to as the restoring force, is equal to the negative kx. Now, why is it negative? If we go back to our drawing here, if we pull the mass to the right, the displacement is to the right, but the spring wants to pull it back to the left. It's a restoring force. It's always trying to restore it to the equilibrium position. So the spring force is to the left, so we need to end up with a negative value. So it'll be a negative kx, which will show that the force goes to the left. Same thing if we were to take and compress the spring. So if we compress the spring this way, now we have a negative x. But our restoring force goes to the right, which is a positive value. And so if we have a negative x times a negative, we end up with a positive number. And so that negative in front of the kx is just to give you the correct direction for the restoring force or the spring force. Okay, so I already mentioned this. Fs is referred to as the restoring force, or the force of the spring. And the negative sign is there because the restoring force is directed towards the equilibrium, and it's opposite to the displacement. And by putting the negative in there, we get the correct direction for our spring force. Work and springs. Well, work is force times distance. But when we look at our graph here that we had earlier, we have force and we have x on this, the x-axis. And so as we go this direction, we have a direct proportionality between force and x. But if we're doing work equals force times x. But you can see, just using regular graphing techniques, when you take fx, you're finding the area underneath the line. Well, because it's a direct proportion, the area underneath the line is half of a triangle. And so the equation becomes work equals 1/2 Fx. So what we're going to do is, we used Hooke's law earlier, or saw Hooke's law earlier, force equals negative kx. We're going to substitute negative kx back into force, and we end up with the work of the spring equals a negative kx squared divided by 2, or negative 1/2 kx squared. Well, we know from our work energy theorem that the work done against the spring has to be equal to the energy gained by the spring. And so we can just change the work S to potential energy. We'll drop the negative sign because energy is a scalar quantity. And so it has that much energy whether the spring is compressed or stretched. There's no direction with energy. And then we can look at our conservation of energy equation, and we're just going to add another piece to it. So potential energy of gravity initial plus potential energy of the spring initial plus the initial kinetic energy is going to be equal to the final of all three of those energies, assuming there are no non-conservative forces involved. That is true. Okay, let's do a couple problems dealing with spring potential energy and the conservation of energy and the energy work theorem. So example 5.9, we have this spring that has a spring constant of 400 Newton meters. And for the first part A, it's going to be frictionless. So if it's frictionless, we can ignore the mass and we can ignore mu k. That comes into a later solution in the problem. So we have pulled the block 0.5 meters to the right. The spring now is going to have a pulling force that's trying to pull it back to the left. And when there's no friction, we can ignore the normal force and the force of gravity. because they're working perpendicular to the forces involved here. So then part A, we are supposed to find what is the velocity when the block travels past the equilibrium position. And so to do that, we're just going to say that the initial energy, which is the potential energy stored in the spring, is going to be equal to the final energy, which would be the kinetic energy as it passes the equilibrium position. And then rearranging for velocity, we get velocity equals the square root of kx squared over m. And plugging in our numbers, we end up with 0.447 meters per second. So this spring is going to oscillate back and forth past the equilibrium position, and it's going to be at 0 meters per second, 4.447 meters per second this direction, and then it's going to go back to 0 and then speed up back to 0.447. So every time it goes past the equilibrium position right here, its velocity will be 0.447. Part B, we are asked to find the velocity at the halfway point, 0.025. And so, again, we're going to use EO potential, the elastic potential energy in the spring when it's stretched the entire length, to the E that it will have when it reaches the halfway point. So at the halfway point, though, it's going to have both kinetic energy and it's going to have spring potential energy. So we are solving for this velocity right here. So we're going to rearrange. First, we're going to subtract this from both sides. And we end up with 1/2 mv squared equals 1/2 k xo squared minus 1/2 k x squared. And then we can multiply through by 2, and it gets rid of all the 1/2s. And then we can divide both sides by m. And we can take the k out and then take the square root, and we end up with our answer. So we would have 400 times 0.5 squared minus 0.25 squared, which gives us 0.001. Can't read my number there. Whatever. Divided by 5. So this number here just represents the number you get when you subtract those. And you end up with 0.39 meters per second. So going back up here, the spring is 0 meters per second, 0.39 meters per second, 0.44 meters per second, 0.39 meters per second, 0, and just oscillates back and forth, reaching those same speeds every time. Part C says, what if we put friction in there? And we're going to resolve part A, including friction. And so the initial energy is going to be equal to the kinetic energy plus the work done by friction as the block is going back to the equilibrium position. And so our initial spring energy is 1/2 kxo squared equals 1/2 mv squared, but now plus the work done by friction, which would be friction times distance. And we remember that friction is mu normal and normal is mg. So for friction, we're going to substitute in mu mg. So then we end up with this equation here, 1/2 kxo squared plus 1/2 mv squared plus mu mgx. And we're just going to rearrange for v. And to do that, we're going to do the same thing. We are going to subtract mu mgx from both sides. We are going to multiply both sides by 2, and that'll get rid of the half here, and then it'll put a 2 in front of the mu mgx, and then we're going to divide both sides by m and take the square root. And then plugging our numbers in, as you can see here, we end up with 0.23 meters per second. So again, the key is using the energy work theorem and the idea of conservation of energy to solve these problems. Now we'll go to sample example 5.10. And here we have a trapeze artist, otherwise known as Daryl, the goat. And Daryl starts out 2 meters above and is going to fall down to the springboard. Daryl has a mass of 50 kilograms, so it's a pretty big goat. The spring constant for the springboard is 8,000 Newton meters. And we are to solve for how far the board gets compressed. So the idea here is I'm going to call the final position that the board ends up in as my zero height. And then my gravitational potential energy will be from 2 meters down to the original position of the board plus that distance it gets compressed. So that's my total height to begin with. So it's not 2 meters. It'll be 2 meters plus whatever that compression distance is. And then if I do that, we can use the work energy theorem again, law of conservation of energy. The initial energy, mechanical energy, has to be equal to the final kinetic energy. And the final kinetic energy will be, all of this gravitational potential energy will be put into work done against the spring. So we have mgh equals 1/2 ky squared, ky2 squared, where h equals y1 plus y2, and I'm calling 2 meters y1, and I'm calling this compression distance here y2. So then, sorry about this. So then putting this stuff, expanding our equation, putting this in for h, we see this as our equation. So it's just the same equation with the y1 plus y2. And then I'm going to multiply mg into all of that. And then I am going to subtract the 1/2 ky2 squared from both sides. And I end up with this quadratic equation right here. Well, then I'm going to put the numbers in to figure out my numbers in front of the y2s. And so 1/2 times 8,000 gives me a negative 4,000 y2 squared, plus 50 times 9.8 gives me 490 y2, plus 50 times 9.8 times 2, which gives us 980. So then here's the quadratic equation, and we just plug our numbers in. B is negative 490, and B here again squared, minus 4 times A times C, divided by 2A, which would be 2 times negative 4,000, which gives us negative 8,000. Then when I put that into my calculator, I get 2 different numbers. So here's my work. I end up with 0.56 meters and a negative 0.437 meters. And the reason I know the 0.56 meters is the correct solution is because when I set up my initial drawing, this distance here, the bottom position, I call this my reference point 0, and all of these numbers are positive. And so it has to be the 0.56. Okay, let's do one more sample problem here to finish up our notes on this section. On this one here, we have a block that has been pushed against the spring, distance x1. The spring has a constant of 625 Newton meters. The compression is 0.1 meters. The first thing we're supposed to solve for is how far up the ramp does it go? Well, what's going to happen is, as this box slides across this frictionless surface, it has to end up with the same gravitational potential energy here that it had for spring potential energy here. And so the first thing I'm going to do is I'm going to solve for height. And then I can just use sine 30 equals height over distance to find our distance. So just a little trigonometry to find the final answer. So EO is our spring energy. It has to equal our final E, which is our potential energy. And rearranging this for height, I get kx squared over 2mg. Plugging our numbers in, I get 0.638 meters. That is not our answer. That's how high it is. So now I have to find this distance. So I'm going to use this triangle right here to solve for it. 0.63 meters is the height. 30 is the angle. I'm going to solve for d. So d will equal 0.635 divided by sine 30, which is 1.28 meters. So it's going to slide for 1.28 meters up the ramp. Part B, we are supposed to solve for the speed when it is halfway up the ramp. And so if it's halfway up the ramp, our height will be 1/2. And so I'm going to use the same thing here. I'm going to go take the potential energy we had at the top of the ramp, and then I'm going to call that my initial energy. And then I'm going to say that has to equal the energy, the potential energy halfway up the ramp plus the kinetic energy halfway up the ramp. So mgh equals mgh2 divided by 2 plus 1/2 mv squared. The m cancel out, which is nice. And then rearranging for v, I end up with v equals the square root of 2gh. And that's very familiar, right? Square root of 2gh, we've seen that many times. But now we're going to plug in minus gh. And so 2gh minus gh gives us just gh. And so then it ends up being just the square root of 9.8 times 0.638, which is 2.5 meters per second. I hope this was helpful. Notes chapter 5.4. Thank you for watching. We'll talk to you again later.